Today we'll look more at logarithmic functions, and in particular their graphs. So remember that if we want to define a logarithm, our domain has to be positive numbers, the base of the logarithm has to be greater than 0, and we still don't want it to equal 1. Then we say f of x is equal to log base a of x is called the logarithmic function with base a. And the way that we evaluate logarithms is by undoing them and turning them into exponentials. If some y value is equal to log base a of x, this happens if and only if we can move the log to the other side. It becomes an exponential, and we have the same equation now, but x equals a to the power y. Now if you look at your calculator, you'll see that the logarithm buttons are rather limited. As a matter of fact, your calculator only does two different kinds of logarithms, and those are the common log and the natural log. The common log always has base 10. If you see a button on your calculator that just says log and has no base, then it's always going to be 10, and it will never be a different number. On the other hand, if you look at your calculator and you see something called ln of x, or natural log, this is a log with base e, and natural log of x has a lot of applications, so we put a button on the calculator because we'll be using it quite a bit. Now before we look at graphs, let's look at a couple properties of logarithms, and we can see how these help us evaluate any log and some nice relationships with exponentials in general. The first logarithm says that log base a of 1 is equal to 0. This is true because if we undo the log, what this says is that 1 is equal to a to the power 0, which is always the case. Any number to the power 0 is always 1. Next, log base a of a is always equal to 1. Again, if we undo the logarithm, what this says is that a is equal to a to the power 1. Property 3 says a very similar thing. It says that if we have log base a, and inside the parentheses we put some exponential a to the x, where the base of the logarithm and the base of the exponential are the same, then everything sort of cancels out and we're just left with x. Again, this makes sense because if we undo the logarithm, what this actually says is that a to the power x is equal to a to the power x, which is obviously true. As well, this works in reverse. If we have an exponent and we have a logarithm in the exponent, then that cancels everything out and just equals x. Now we're going to move the base of the exponent here to the other side. And if we do that, then the left-hand side becomes log base a of x. And that's what was the exponent before. And if we move an exponent to the other side, it becomes a logarithm. So this says log base a of x is equal to log base a of x, which again is just obviously true. Now, property 3 can be summarized as saying that these are inverses of each other. So property 4 is the inverse property, and what it says is that if we have some function f of x is equal to a to the x, then the inverse, f inverse of x, will always be log base a of x. The base of the exponent becomes the base of the logarithm. And we can sort of switch sides and go back and forth to cancel out and build logarithms. Property 5 is also quite nice, and it's one of the ways we can evaluate logarithms rather simply. This is called the one-to-one property, and what it says is that if we have an equation, and we have two logarithms with the same base on both sides, then they're able to cancel each other out, and we can just take whatever's in the parentheses and set them equal to each other. Log base a of x is equal to log base a of y, if and only if x equals y. And this is also true for exponents. If we have two exponents on either side of an equation, and they have the same base, then it just cancels out and we can set the exponents equal to each other. We'll use property 4 and 5 a lot when we start evaluating logarithmic equations, and we'll see their use in great detail. Now that we have these done, let's move on to looking at graphs of logarithmic functions. And we'll see that these are very much based off of the graph of exponential functions. So remember that exponents and logarithms are inverses of each other. So the functions work as inverses as well. Therefore, if we want to graph some logarithm, all we have to do is look at the graph of an exponential and change the x and the y column. So the x values become y values, and the y values become x values, and we can see that these are reflected. So if we wanted to do this, maybe on the same graph here, and we remember that inverses are reflected over the line y equals x, then right away we should be able to graph down a logarithm. First we look at the top entry. It says when x is -2, y is 1/4, and now this changes. When x is 1/4, y is -2. So about some point here, and this is 1/4, comma, -2. And the same happens for every other point. The point -1, 1/2 on the exponent becomes the point 1/2, -1 on the logarithm. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And 2, 4 becomes 4, 2. So 1, 2, 3, 4 over an x. 2 up for y. And now we have the shape. And hopefully when we graph it down, we can see in nice detail here how these functions really are just reflected over that orange line and line up quite nicely. So with this in mind, let's try graphing this without the exponent there, and we'll see what we get. So, without the exponent, we should still make a small change here. Instead of saying f of x equal to log base 2 of x, we'll say y is equal to log base 2 of x. And then we'll undo the logarithm and say 2 to the y is equal to x. Once we have it in this form, the next step is to plug in y values to find x values. And we'll plug in the same y values now that we plugged in before. So -2, -1, 0, 1, 2. And then to find the x values, we just run them through 2 to the y equals x. And we'll see a nice line up with the exponent here. So 2 to the -2 power is our x value, which is 1/4. 2 to the -1st power, 2 to the 0 power, 2 to the 1st power, and 2 squared. This is the only function that works in reverse. We plug in y values to find x values. And now that we have these down, let's graph them on here, and we'll see the same picture again. When x is 1/4, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. And when x is 4, y is 2. And there we go. We'll try that again. We have a nice boomerang shape, but it's sort of going down now, and it goes down very quickly, and then it kind of lags as it moves out, and it slowly approaches infinity, but logarithms lag and exponentials explode. Now we can state some general facts about the graph, and they're very closely related to the properties of exponentials. And from the graph, we can probably guess what the domain and range is going to be. And we can see that there's this vertical asymptote happening at y equals 0. So let's get these down nice. And again, these are true for any logarithm. So the domain is always 0 to infinity. We can only plug in positive values. The range, however, is going to be negative infinity to positive infinity. We'll eventually hit every y value, and we can see that on the graph here. As it moves out in x, it's slowly moving up and up and up, and there's nothing to stop it from reaching infinity. It has an x-intercept at 1, 0. Again, the graph is always increasing, and now we have a vertical asymptote at x equals 0, and we'll never be able to cross that. So this is only defined in just half of the graph. Now we can see here that, like square root functions, we can only take logarithms of positive numbers. So therefore, we have the same domain problems that we have when we look at square roots. This means that if we wanted to find the domain of some logarithm, we have to take the inside, set it equal or greater than or equal to 0, and solve. So let's find the domain of f of x is equal to the natural log of x minus 5. And all we have to do is take whatever's inside the parentheses right here, make sure that's greater than or equal to 0, and solve. This one's easy. All we have to do is add 5 to both sides. And we see that our domain is all x values greater than or equal to 5, or 5 comma infinity. Now with logarithms, we don't want to use the equal to, we just want straight greater than. So square roots are greater than or equal to. Logarithms, we use parentheses, and we just use greater thans. In the next section, we'll look more into these properties of logarithms, and we'll start to see how we can solve equations using the inverse property and the one-to-one property. And then we can start looking at nice solutions and graphs in general.